in the last video, I went over the simulation loop that we'll be studying. So here is a very quick review. So this simulation right here is supposed to model reality. It divvies time up into many small little instants where things happen and nothing happens in between. At every one of these time steps, it does the same loop of calculations to every piece of matter in the simulation. It calculates forces, which we haven't really talked about that much yet. Then it uses those forces to modify velocity. And then it uses the velocity to modify position. So the golden rule here is that whenever two pieces of matter interact, they always do so with a force. And those forces are always equal and opposite. Okay, so the simulation loop I'm showing here is actually slightly different from the one that I showed in the last video. The difference is that this one, or the one that from the last video, calculates the forces inside of this loop right here. And this one actually calculates the forces separately up here, and then does the velocity and position modifications. So the reason for this is a little bit silly. If two objects feel a force, right, that depends on, say, like the distance between each other, like the attractive forces in the last video, but then one of the two objects gets to move a little bit before the other has a chance to calculate its force, they'll feel unequal forces during the same time step, right? Because like one will move, and then this one will calculate its force, and they'll be different. And this violates the one thing that I said that forces always do. They're always equal and opposite. So this simulation loop, while slightly more complicated, is more accurate. I just wanted to clear that up. The other difference is this, the sum up all the forces bit. In the last video, we talked about how forces work, but we didn't talk about what happens when there are more than two objects interacting with each other. The rule here is that forces add. So if like one object is feeling forces from like two other objects, say like a force of 10 and a force of -4, then the resulting force that you would use at this point in the loop would be 6, so 10 plus -4. So yeah, those are the main differences here. In this video, I want to introduce a specific kind of force: collisions, like that. This is not a fundamental force. It's actually a combination of lots of complicated interactions, some of which we might talk about later in the series. But despite that, it is an important kind of interaction. It's one that illustrates very nicely a couple of extremely important ideas. So what is the collision force? The goal here is to come up with something, to come up with an expression that we can just plug into our simulation loop up here and say go. Now, I want this expression to be physically motivated, but I don't really care about perfect accuracy. This video series is mostly about concepts. So what I did is I went onto YouTube and I found a couple of slow-mo videos of tennis balls, like kind of bouncing around and colliding with each other. I tracked their positions over a number of video frames, and then back solved to get an idea of what shape the force should take. And then I wrote it down on a piece of paper, and I lost the piece of paper. And I really didn't want to do that again, because that was crazy boring. I didn't like doing that, and so I kind of just made something up based on what I remember it to be. It's a very scientific series, as you can see. The gist of this thing is that when you calculate the distances between the objects and the maximum distance that they can, the distance between object centers here, and the maximum distance that the centers can be at before they're touching. If they're farther than that, the force is 0, and if they're closer than that, they feel a force. As the objects get closer together, the force they feel gets larger in magnitude. There is one thing that I'd like to bring attention to here, and that is the this position minus the other position bit. The way this works is that each object, when it's at the stage when it's time to calculate its own force, it plugs its own position into the this parameter and the other position into the other parameter. So for the right ball, it's going to be the right position minus the left. And for the left ball, it's going to be the left position minus the right. So for the what this means is that for the right ball, this quantity is going to be positive, right? Because it's the right object minus the left. So it's a more positive position minus a more negative position. So this distance right here is going to be positive, and that is going to cascade through this expression to get a positive force. For the left ball, this quantity will be negative, and so it's going to cascade through here, raise it to an odd power, and divide by it, and get a negative force. So I admit this is maybe a little bit odd. Some of you may even see this as clever, because it takes two different cases, the left case and the right case, and it handles them both with the same expression. Some other people may see this as beautiful or elegant, because this way of writing down the forces doesn't have to differentiate between the two cases, the left case and the right case. It treats both exactly the same, which lines up with people's intuition that physics should, it should act the same both for you and for me, right? But some other people will probably see this as like unclear or needlessly confusing. He's like, what's with all this, distances which are actually can be negative and like a chain reaction that can get negative forces. But that's a little wacky. For those people, I don't know. I guess I'm sorry. These lectures are going to be like that sometimes, but also like to remind you that confusing is often just a function of familiarity. The more you see tricks like this, the more comfortable you may become. I think these kinds of things are useful, and yeah, we're going to be going with this. So yeah, that's the collision force, and here it is in action. I want to analyze this with you. Put some numbers to things, start making graphs. In the last video, we talked very qualitatively. This velocity is larger or smaller. This, this force is larger or smaller, that kind of thing. But I like graphs. I'm a visual person. So what should we graph? Well, there's only really a handful of pieces of information in this loop. Each object has a mass, but those don't change over the course of the simulation. Graphing those would just kind of be silly. Clearly the simulation loop, clearly the simulation doesn't vary mass at all. The loop from a couple slides ago does not have a line saying something like mass plus equals something, right? The quantities that do change over time are time, of course. Time ticks forward each instant, but also the force and the position, the velocity that each object is feeling also changes over time. So there are only 4 things here. So to start, I suggest that we just graph each of these major variables by every other variable. Right? There's only 4 of these, so when you remove duplicates, that's only 6 graphs. Force over time, position over time, velocity over time, force over position, force over velocity, and velocity over position. So yeah, let's look at them. Here are the first 3. We have our original simulation in the upper left, just so that we can, have something interesting to look at, have something to orient ourselves. We have our force over time graph right here, our position over time, and our velocity over time. So let's look at this one first. So notice how the force graph has a perfect reflectional symmetry about this horizontal line. Hopefully that makes sense. At every point in time, the red object and the blue object feel the exact same force. Just one is negative and one is positive. So, so that's good. Then there is the position over time graph. So there's not much here to say, I think. I would like to point out that in the moments where the objects feel no force, where they're not colliding, the graph looks like straight lines, right? And the moment that the graphs, or the moment that the objects are colliding, they kind of look like curves, right? They have these smooth curves connecting these straight lines. Also, notice how there's a sort of diagonal symmetry about here like this. Like if you took this red one and you flipped it over this like diagonal line that kind of cuts through here, you'd get the blue graph. That's kind of interesting. But we're not going to talk about this. I'll save this one for a future video. Now let's look at the velocity over time graph. So here there is another very clear line of symmetry, right, going down right here. But it's maybe not super obvious why this one is symmetric. Before moving on from these three graphs, I want to run another simulation, well, the same simulation actually, but now the blue ball has twice as much mass as last time. So remember from last time, from last video, the role of mass in interaction with forces is that they respond less to the same force than an object with less mass. The functional result here is that with a repulsive force like collisions, heavy objects tend to sort of barrel through smaller objects. And when at rest, smaller objects tend to kind of bounce off of them. So we can kind of see that happening here. This blue object is able to use its mass to sort of push through the red object and kind of keep going, though at a lesser speed. So back to the graphs. For the force graph in particular, they're being shown on the same scale as before, so I can kind of switch back and forth between them like this. So notice how the force graph in our new simulation is wider than the last one. It's wider horizontally. So this is because the left object is actually now wider, so it's initiating the collision earlier, right? So maybe that's a bit of a silly difference. Also, notice that the red and blue forces are still symmetric. Remember, when any two objects interact via a force, the force is always equal and opposite, even when the masses are different. In that collision force I showed earlier, I did not take mass into account, just the distance between the centers. So that's good. That makes sense. For this one, again, I don't really have much more to say other than to notice how much less sharp these curves are. If I flip back to them, yes, the curves in the new one are a much smoother, corresponding to how much wider this collision is happening over. Also, that symmetry I talked about kind of went away. Well, maybe not went away. There's still some kind of very obvious something happening here, but it's maybe not as obvious anymore. And now the velocity over time graph. So the symmetry that we were going for is still kind of there. It's very reminiscent of the reflectional symmetry we had, but not quite. It's almost like you just took this red object and you flipped it, but then you squished it a bit. It's almost like what happened. I want to talk about this. So to explain this, let's go back to the simulation loop. So here I have made one last modification to the loop. I have not changed what it does. I've just rearranged it a little bit. Instead of doing these calculations and accumulating them in one step, so doing velocity plus equals force divided by mass times dt, I am separating out the calculation and the accumulation. And I'm giving the intermediate calculation here a new name so I can refer to it later. dvel here stands for the amount that we're changing velocity in this particular time step. So it means so you'll hear me refer to it as delta velocity, or the difference in velocities. Same thing with this d post, this delta in position, or the differences in position. It's the amount that position changes over this time step. These two values are going to be very small. They're going to be like 0.001 or something like that, whereas your actual position and velocity are going to be normal numbers like 1 or 2 or something like that in these simulations. What I want to draw your attention to is this line right here, this new line that we've made. Delta velocity is equal to force divided by mass times dt. So I've rewritten it up here. Rearranging this line, bringing the mass to the other side of this, you get mass times delta velocity is equal to force times dt. So we know that dt is the same for each time step. And we know that at each time step, the forces between the red and the blue objects are equal and opposite in sign. So if we write that out here, what that means is that the quantities delta velocity times mass for the blue object and delta velocity times mass for the red object are also going to be equal in sign, right? Because for the blue object, it's going to be dt times a negative number for the blue object, and for the red object, delta velocity times mass is going to be that same number that we had here, but positive this time, times dt, because these forces are equal and opposite. So this quantity here, the blue delta velocity times the blue mass, is going to be equal and opposite to the delta velocity times mass of the red object. So this should suggest something that we should maybe try to do with the velocity graph to maybe recover its symmetry, maybe multiply by the mass. Well, what would that do? Well, sure enough, if I scale the velocity over time graph by each of the object's respective masses, the symmetry comes back. So it doesn't quite look the same. It almost looks like this one was scaled up and also shifted, but that's just because of how the multiplication works. For this blue object at the end, it is sitting above the 0 line by some amount. So when you double it, it's going to get higher. This one, when it doubles, it's going to go like way up here. So that's kind of why it looks like it's shifted up. But you can see very clear line of symmetry now has been recovered, as opposed to with the velocity over time. When you scale by the mass, you recover the symmetry. But we were just talking about the delta velocities times the mass being equal and opposite. Why would this imply that these graphs should be symmetric? Why would one imply the other? Well, if in one time step this quantity, the mass times velocity, for the blue object decreases by like 8, then it must increase for the red ball by 8. And if in the next time step it decreases by like 10, then for the red object it must increase by 10. And so over the course of 2 time steps, it will decrease for the blue object by 18 and increase for the red object by 18. So therefore, over the course of 2 consecutive time steps, it's not just the delta velocity times mass over a single time step that are equal and opposite. It is the delta velocity times mass over any arbitrary set of time steps that are also equal and opposite. So in other words, if you just pick any 2 points in time, the amount of mass times velocity that the blue object loses must be gained the exact amount of mass times velocity must be gained for the red object, even though the two objects have different masses and different velocities. By the way, this quantity, mass times velocity, is fairly important, and it has a name, which I've kind of given it away a little bit over here with the graph labels. It's called momentum, and this symmetry that you're seeing here also has a name. It is called conservation of momentum. So this name reflects a different way of looking at the relationship. Instead of the differences in momentums between 2 points in time being equal and opposite, the traditional way of looking at this is that whatever momentum is lost by one object is gained by the other. So, in other words, the total momentum of all of the objects, the sum of their momentums, is constant, right? Because if one of them loses, 18 momentum, and the other one gains 18 momentum, then if you were to add their momentums between, at the first time step and the second, they would be the same because the plus 18 and the minus 18 would cancel out. I want to dwell on this a little bit more. Just to go through it a little bit slower, the velocity of an object at frame 100 is going to be the initial velocity plus the delta velocity 0 plus delta velocity 1, all the way up to the delta velocity 100 is included here because we are measuring velocities and delta velocities at the ends of the loop, not the beginning. So I mean that's obvious, right? The velocity at this point is just the initial velocity plus all of its changes. So if you were to multiply both sides of this equation by mass, you would have mass, that object's mass, times its velocity at frame 100 is equal to its mass times its initial velocity plus its mass times its delta velocity 0 plus its mass times its delta velocity 1, on and on down, right? But we know that whatever the mass times delta velocity of a delta velocity 0 of the blue object is, well, for the red object, the mass times delta velocity 0 is going to be equal and opposite, right? Same for mass times delta velocity 1. Whatever this is for the blue object, it's going to be equal and opposite for the red object. So what that means is that since each of these lines are equal and opposite for the two different objects, their sums, the sum of all of these items, are going to be equal and opposite for the two items. So if you were to say add the blue ball's momentum at velocity 100 and the red ball's momentum at velocity 100, it would be exactly equal to the momentum of the blue ball at time step 0 plus the momentum of the red ball at time step 0 plus a whole bunch of terms from the blue object, for like all of these ones here, plus a whole bunch of terms from the red object that would all end up canceling out. So that is what conservation of momentum is, that the sums of momentums of the red and blue objects are going to be the same at every time step, no matter how far apart in time they are. So that's pretty cool. But before we continue, I want to mention that I haven't forgotten about the other graphs. We won't be going into them in this video. We're saving these for next video. It will turn out that this graph in the upper corner is this force over position graph will be very important. It's probably the most important of all 6 of the graphs presented here, actually. But that's for next time. Back to momentum. So all that stuff about the sums of momentums being equal is pretty cool and all, but so far in the last 2 videos, we've only talked about pairs of objects. What happens if we throw another one in the mix? So here we have 3 balls in play, all have the same mass colliding with each other. So we're going to start out simple. Here the 3 balls undergo 3 distinct collisions, one here, one there, and then one here. So let us look at our graphs. So here are our graphs. For the first graph, you can very clearly see the 3 collisions. So notice how they're different sizes. There's this kind of like, mama bear, papa bear, baby bear kind of 3 collisions going on here. This is because the collision of the balls are moving at different speeds. This one is the biggest because I guess I'll wait for the thing to come around again. But when this one happens, the red and green ball are actually moving towards each other. So they're, as opposed to in the beginning when it's just the blue ball moving, or in this end where it's just the red one moving. And because they're moving towards each other, they're able to kind of squeeze closer in, and they're able to feel a larger force. But still, all of the graphs are perfectly symmetric, right? They're feeling forces that are equal and opposite. For the position graph, again, you can see the 3 collisions very clearly. One happens here, one happens here, one happens here, corresponding to these like kinks in the graphs. Between the curves, they are nice straight lines. All right. For the velocity over time graph, again, you can see kind of what was happening in our first example, where the velocities kind of swap. So you can see this happen 3 times. Once right here during the red and blue collision, the red and blue velocities swap, and then the red and green velocities, and then the red and blue velocities swap again. Okay. Well, what happens if the collisions aren't distinct? What happens in this case? So, remember what I said earlier about forces adding. The red ball, when they're all squished into each other, is feeling the force of collision from both the blue ball and the green one, and they're being added together. So if the contribution from the blue ball is like 5, and the contribution from the green ball is like -7, then the total force that this red object is feeling at that time step is going to be -2. Okay. So the graphs again. The force over time graph is all muddied. There's no clear delineation between the collisions. But if you look closely, it's still sort of balanced, right? Like you get like these peaks and these peaks, and during this little bit right here, there's a little bit of stuff happening above the horizontal line and a little bit of stuff happening below. And that's correct. At every time step, every pair of objects is sharing equal and opposite force. But that also means that the sums of all of the forces between all the pairs of objects is going to be 0, right? So this force graph should always be balanced around 0. Let's see what else. Instead of a position over time graph, which it's been kind of boring this whole time, I have the velocity over time graph and the momentum over time graph. In the velocity over time, you can see that the graph starts maybe a little bit lopsided in the positive direction. You have this line up here, and you have the red one kind of up here as well. So it's maybe a little lopsided up here, but when it ends, it's maybe a little lopsided in the negative direction. And you had both of these graphs down here while only one's up here. So the sums of their velocities, or their averages, if you will, is not conserved. But moving over to the momentum over time graph, that is not the case. And look at like the beginnings and ends. This distance right here is about this distance right here. It's hard to tell exactly because not as I'm measuring my fingers, but the momentum here should be the sums of all the momentums here is exactly equal to the sums of the momentums over here, and you can kind of see that this one is a bit balanced, is about the same balance as well. Like both of these are about like this height. You can see both of them are about half of the height of the screen one. So in so yeah, the sums of the momentums here about cancel out on both sides, in about the same amount. Just with finger measurement. But we saw from the derivation that this is actually exact. These sums of the momentums at one time step should be the sums of the momentums at some other time step. But we haven't actually worked it out for the case with 3 objects. So why exactly is this the case? Well, again, it all comes down to our simulation's rules. The red object's delta velocity is going to be equal to the force it's experiencing during the collision divided by the mass times dt. But when the whole thing is happening, when all 3 objects are colliding at once, the red object is feeling a force from both the blue object and the green object, a positive force from the blue object and a negative force from the green object. If we were to add up all of the momentums, all the masses times, not the momentums, all the masses times delta velocities, because momentum is mass times regular velocity. If we were to add up all the mass times delta velocities, what would you get? Well, for the blue object, you'd get, like we talked about, is the negative force times delta velocity. For the green object is going to be the positive green force for the delta times delta velocity for the green one. And for the red object, well, it's this thing that we were just talking about here. It's going to be a positive blue force plus a negative green force times dt. And so, after multiplying this dt inside here, all of these things cancel out, right? The positive negative blue, the positive negative green, it all cancels out. It all goes to 0. So the same thing is happening here with 3 objects that was happening with 2 objects. And so this right here is conservation of momentum. The sums of all of the objects' masses times their delta velocities, when you sum them over every object, is going to be 0 at every single time step, always, as long as your forces are always equal and opposite and all accounted for. We define an object's momentum to be its mass times its velocity, and the sums of momentums over every object is constant at every single time step. Whatever the sum of all the objects' momentums are at the very beginning of the simulation when we first start is going to be exactly what the sums of the momentums are at any other later point in time, as long as we are always taking into account all of the forces and all of the objects. So yeah, this is conservation of momentum. Before we end, I want to talk about one last thing. I don't want you to get the impression that the stuff we talked about just applies to our collision force, the one that I introduced at the beginning. After introducing it, I never really brought it up again, really. And the derivation of the conservation of momentum does not rely on any of its properties. So even though I just kind of made it up, it's not like set in stone. Like, the conservation of momentum does not rely on it. As long as your forces are equal and opposite, which they should be, conservation of momentum always works. And so to demonstrate, I cooked up a very strange looking collision force that kind of looks like this. Something really wacky, and it has no basis in reality. And you can see down here with the velocity graph, has a fairly strange shape, has like these weird kinks in it. But still, the momentum symmetry is still there. If you take this red one and you scale it down by 2 and you flip it, you get the blue one. Obviously, right? And you can see it right here. So conservation of momentum is working here too. So yeah. That's momentum. We'll come back to this eventually a couple times, I think. Momentum is a really important concept. One of those things that throughout physics you can never really get away from, right? And the next one of these videos is going to be about another important concept, kinetic energy. In this video, we looked at graphs and noticed symmetries and saw how they came from the simulation loop, and all of that is just a warm-up for next time. It's going to be good. So I'll see you then for kinetic energy from the viewpoint of simulation. See you then.